Alright, welcome back to part 2 or 3 or I don't know, all the parts are starting to meld together. But the next part is simple machines. We're going to talk about inclined plane, wedges, and screws. Now these are all basically the exact same thing. They're all basically inclined planes. So if you can understand inclined planes, you can basically figure out everything else. And I'll explain how that's true in a minute. Now, just a little recap. Inclined plane is just a ramp. A wedge is basically two inclined planes that are next to each other. Okay, and then a screw is basically an inclined plane wrapped around a cylinder that just keeps going over and over and over and over. So it's basically just a bunch of it's one inclined plane wrapped around a cylinder. Okay, so let's move on. Mechanical advantage again is the ratio of magnitude, resistance, and effort forces. Well, then move it, kiddo. You got hands. God gave you two perfectly good hands. Well, I know, but you'll be fine, kiddo. You're a strong, independent woman. Right? You want to be a strong, independent woman? Well, that's too bad because you are one. Alright. There's also the ratio of distance traveled. This is an important one. Remember that AMA is FR over FE, and IMA is a reciprocal of that, DE over DR. Okay, the distance of the effort over the distance of the resistance. Because remember, either you're trading off forces for distance or distance for force. Now, just a refresher course, the actual is always going to be less than the ideal, alright? Always and forever, alright? That will give us a percent efficiency by dividing AMA over IMA. Okay? Cool. Mechanical advantage, 4 to 1 is greater than 1, so this mechanical advantage is greater than 1, which means that we are putting less effort into our system. Okay? But we are traveling 4 times the distance. Okay. The magnitude of force is the effort 4 times less. We covered all that. We talked about this. Greater mechanical is less effort required, but greater distance. Less than 1 is greater effort force required, like weights and staplers, but you travel less distance. Can never equal 0, because that would mean that something has moved 0 feet or has been weighs 0 things. So here, if you want to do that real quick, AMA is FR over FE, right? If anything was 0, this wouldn't work because nothing. That means that something isn't happening, and it's not a system then. Sure, you can help me, kiddo. Come on up. Yes, you can have the marker. No, you can't draw right now because I'm talking to my class. You want to say hi, class? Okay, you're going to be shy. Alright, again, ideal mechanical advantage is D over DR. Actual mechanical advantage is FR over FE, and then the percent efficiency is the ratio between the two. Smaller always being on top. Inclined plane is a flat surface set at an angle or incline with no moving parts. There's nothing moving. The simple machine itself isn't moving. Now, things move around the simple machine, but the simple machine itself does not move. Okay, it is merely a passive system that other things move around. Okay, it's able to lift objects by pushing or pulling the load. So, in this case, we're going to calculate our ideal mechanical advantage, and the equation is pretty simple. We're going to get the distance. Let me see this. The distance traveled by the effort. In this case, that 15 feet along the hypotenuse of the ramp. Now, when I say hypotenuse, it's because if I look at this from the side, I am making a right triangle, with this side being 4 feet and my hypotenuse being 15 feet. Now, my load always travels along the hypotenuse. Okay? Does that make sense? Well, hold on, kiddo, because I'm talking. So, it always travels along the hypotenuse, because if it did this, it would not be an inclined plane. Okay? I have to be traveling at some angle, here, theta, that I don't know off the top of my head. Okay? So. Not like that. Okay, kiddo. You're killing me, Smalls. I gotcha. Alright, so It always travels the hypotenuse. That's going to be important as we move forward into things. So, distance traveled by the effort is L. You okay there, sweetheart?
This
hurt you?
me. No, this stops me.
Divided by the distance of the...
Daddy,
What?
This stops me.
Okay, are you okay? Okay, great. So, the distance traveled by the force. So, if I was also... Maeve, I have to talk. Okay? All right. So, if I'm looking at this, if I was to draw this system, okay, let's say I'm just going to use a free body diagram, which is just a ball. There are a couple of different loads on here. Okay, there is the effort force at which I'm pushing. This is my force of effort. But there's also a hidden force that we can't really see, and that's gravity. Which way does gravity always pull? It always pulls straight down. Force of gravity. That's why this value is the value of the resistance. Okay? Because gravity, if I was to move these, gravity would be vertical, which would be here. And notice that the effort force is going at an angle along parallel to the ramp. Okay? That's why my equation is the hypotenuse. Well, I'll use their symbols. The hypotenuse over my my FG or my H here. Okay, I don't like the way they did these letters, but so the slope over the height. What is the ideal mechanical advantage of this plane? Where I take the slope, which is 15, and divide it by the height of the ramp, which is 4, which is equal to 3.75. Or if I round to the nearest tenth, 3.8. Okay. All right. What is the AMA of the system? Now this wasn't in the previous, but I can still do it just like normal. Remember, if I drew this as is, as a free body diagram, here's my system. Here's my force of effort. Is straight down. Force of gravity. Fg is equal to the load, so 50. It's being pulled straight down by gravity with 50 pounds. And my effort force that I am applying is 20 pounds. Okay? So I simply just follow this. Effort is 50 over, resistant is 50 divided by the effort, which is 20. Okay. Those cancel, so I'm left with 5 over 2 or 2.5. I'm sure it's going to do it for us. 2.5. Boom. Okay. What is the efficiency of this plane? Well, I take my smallest, which is always my AMA. That always goes on top. 2.5 divided by what I got last time, which was, what did I get, 3.8 after rounding? So 2.5 divided by 3.8 is 3.75 since they did it. 67%. This is a 67% efficiency. Okay. Now, that might not be talking about the inclined plane, because remember, this is a passive system. So why are we losing... Where are we losing efficiency? Probably the friction between here, the wheels and the road, as well as there's another friction point that we have to talk about, and that's the bearing inside the wheel. At those 2 points, the friction between the wheel and this, now there's 2 types of friction. There's kinetic friction and there's static friction. Basically, if you ever try and move a chair, it's always harder to start pushing the chair across the floor than it is once the chair is moving. It gets easier. So you get static friction is always greater than kinetic friction, but we're not really talking about that right now. But there's 2 friction points: the bearing in the wheel and the ramp. Now both those combined, because this is 4 wheels, so that's times 4, and there's 4 wheels, so that's times 4. So it's really times 8 possible friction points that all lose efficiency. They all lose efficiency in the system, and that's why this drops so rapidly down to 67%. The easiest way is to reduce friction to improve your systems. But remember, the ramp itself does not affect the system, unless you could slick this down with some oil or something. All right, wedges. Now this is some fun stuff. Okay, basically a wedge is a moving inclined plane. Okay. So it tapers to a thin edge and used for splitting, raising heavy bodies, or tightening, or being driven into something. One of the easiest ones is splitting wood. I use a wedge to split wood. I do this all the time for my fireplace. You just put a wood on something else, you put a wedge in it, you hit it with a hammer, boom. Or you use an axe. An axe is a wedge. Or if you ever need to wedge up some paint cans, you use a flathead screwdriver. These are all great examples of a wedge. Now, a wedge is basically just an inclined plane, right? So we have to take the average of both of those, which is the perpendicular length, so the actual, I think it's called altitude of this system, right? Which is 10 inches, okay? Not along the horizontal, but perpendicular to the height, okay? It's a little bit different than the inclined plane, but just keep that in mind, okay? So it's the actual length, the altitude perpendicular to that side, which is 3 inches, so 3 to 10. So, and I do the same thing. Since this is traveling, my resistant is going to be how far this is splitting the wood. So that's my resistant, and my effort is how far is how long my wedge is. That's how much effort I have. Okay, the 3 inches here is how it splits the wood, because it's splitting the wood from 0. So if this is the piece of wood, it's splitting this. Let's say that's the split. I'm going from 0 to 3 inches by the time it travels down. Okay, so I want this to be 3 inches. So that's why that's my resistant force. Okay, so then I take my L over my H, and I get 10 over 3, which is 3.3. My wedge, AMA is the same as everything else. AMA is FR over FE. In this case, since I know my force is going to be 700 pounds to split the wood, and I'm hitting it with 250 pounds, that's my effort force, and the force of the wood is going to be for splitting it. And I get 700 over 250, 2.8 mechanical advantage. The efficiency, same as before, 2.8 over, what did we say it was before? 3.33, which is 84%. Okay? Last but not least is the screw. So it's an inclined plate and wrapped around a cylinder, forming the path and pitch. A wheel and axle used to create rotary motion. So basically what I'm doing is I am turning the inclined plane around something. So change rotary motion into linear motion. Used as a thread fastener, large mechanical advantage, large amount of friction loss. So this is a screw. If you guys, some of you guys are in the robotics program, and we use very much quarter 20 bolts. This is a 1/4 inch major diameter from thread to thread. So from one side of the thread to the other side of the thread. It's called a diameter. The ones we use in the shop are 1/4 inch. This one happens to be a 1/2 inch, so twice as big. The next number, okay, is 20. That means that every 1 inch, so let's say this is 3 inches long. So if this was 3 inches long, okay, for every 1 inch, there's 20 threads. So in a 3-inch bolt, for a 20 pitch screw, that means that there will be 3 times 20, which is 60 threads. So if I count up each one of these, it would come out to 60 in a 3-inch screw. Okay, the pitch is a distance. The pitch is the distance between the rotary of the screws. We won't talk about that right now. But the thread count, so 1/4 20, 1/2 inch 13. If for every 1 inch there are 13 threads in this system. So for every 1 inch, if I counted in this is a 1/2 inch 13. If I count 1, 2, 3, all the way up for 1 inch, I'll get 13 threads. If this is a 3-inch, like I said before, in this example, I would have 3 times 13, which is what, 39. Okay. So the threads per inch, 1/4 20. It's the diameter, and then the threads per inch. So 1/4 20 is 1/4 inch diameter bolt with a 20 thread per inch count, right? Now a pitch would simply be the distance between threads and linear distance traveled by one rotation of the screw. If a 13 thread per inch, then the pitch is 1/13 of an inch, okay? So every time I spin it, it'll go 1/13 of an inch. For the 1/4 20, if I have 20 threads per inch, every time I go an inch, or every time I spin it, I'm going to go 1/20th of an inch. Does that make sense? That is the pitch. Okay? How far will a screw with 13 threads per inch move linearly if turned in one rotation? Well, 1/13th of an inch. All right, mechanical advantage of a screw. Hey, look, a quarter 20. Boom. That means in 1 inch, I'll have 20, and the pitch would be 1/20th. That is the distance between here and here, is 1/20th of an inch. Okay, which is what, 5/10ths of an inch, something like that. All right. So the way this works is one rotation of effort arm, or the circumference, divided by the linear distance traveled during one rotation, which is the pitch. So the circumference of my bolt, which is calculated using the circumference, okay, divided by the pitch, which is, again, 1 over the thread count. So the IMA here is I'm using 2 times pi 8, 8 being the one rotation of the lever arm. Circumference. Where'd the 8 inches go? Oh, an 8. Yeah. Okay, the 8-inch long wrench. So, basically, what's happening here? Let me back up. I got confused. So here's my bolt. Okay, it's a terrible bolt. Let me try again. Also terrible. One last time. There. Okay, that's my bolt, right? That's the top of my bolt. I'm looking at the top down. Okay, I'm going to have a wrench. Here's a wrench. Wow, this is terrible. There's a wrench that is 8 feet long, or 8 inches long, because that's what it says in my next step. So the rotation of the effort arm, in this case, the effort arm is the wrench. Okay, so the effort arm is the wrench, and it tells me the wrench is 8 inches long. And that is the radius. So if this is my screw head, and this is my wrench, you can see that if I went all the way around, I create a circle. So that's my R, is the length of the wrench, in this case, 8 inches long. Okay?
I think that's the O.
Yeah, there's an O. Good job, kiddo.
And a toto.
And a circle. Yeah, they're the same. What is the IMA of the screw above and effort is applied by an 8-inch long wrench? Well, I take the radius of the length of the wrench. Remember, this is my bolt, this is my wrench. That's R, because I went all the way around. I create a circle. That's a bolt and that's a wrench.
Oh.
So 2 pi times the radius is circumference, divided by the pitch, which is 1 divided by the thread count.
1 is the pi count?
1 divided by the thread count. Good job, kiddo. And that is pitch. Can you say pitch?
Pitch.
Pitch. So my answer becomes 1005.31, or if you wrote it in scientific notation, it would be 1 times 10 to the third. I don't know why they decided to do that. 10 to the third.
Yes. I
Yeah.
like that.
Actual mechanical advantage is, so this is going to have a resistant force into my system of 1,200 pounds. It's given to you, and then I am turning with a torque of 35 pounds. So I just simply go ahead and do 1,200 divided by 35 and get 34 to 1. What is the efficiency of my system? Well, 34 divided by 1,005.3, which gives me 3.4. Why is the efficiency so low? Because each one of these threads has friction constantly upon it. I am losing 97% efficiency because that thread is going into my piece. Imagine using an actual screw, not a bolt, a screw into wood. I'm literally splitting that wood with the wedge, as well as each one of those. Here, if you guys take your hand and do this again, right? This is one thread. Yeah, can you do it, kiddo? Good job. This is one thread. So like your right hand is the thread of the screw, one thread. So that's 1/20th of the screw, and the left side is the wood. That heat loss is happening to each one of those 20 threads on that screw per inch. So the more you go, the more resistance, and those just calculate. So if this has a resistant loss, if this one thread has a resistant loss of, let's say, 2, and this thread has a resistant loss of 2, they multiply. And I start losing efficiencies really, really quickly. Compound machines, once I start having wheels and axles, so let's say I have this wheel and axle here into a pulley system, right? I take the mechanical advantage of this system and multiply it by the mechanical advantage of this system to get my compound machine. So let's say this is the wheel and axle. Okay, this is a pulley system 1. Let's say I had a lever. I just take all the mechanical advantage and multiply them together to get my system. And that is all I have for simple machines. Congratulations, guys. I'm going to have some problems up for you today that you guys will have to do, and let me know if you have any questions.